Well, hello everybody. Good morning. Happy spring, and welcome to today's live and livecast presentation of Saturday Morning Physics. It's a very special event today that is sponsored by the Van Loo family. We thank all the sponsors of Saturday Morning Physics. And I want to just take a moment today to thank the people who make this happen. First, I want to thank Carol Raybuck, who administrates this and does everything to make it happen. I want to thank the Demo Lab staff of Monica, who's not here today, Nick, and Connor now, who has joined recently. And I want to thank my co-host, Roy Clark, who's helped organize this. It's my pleasure today to introduce this special Van Loo family presentation. It is 2 lectures by graduate student PhD candidates in the Department of Physics here, Mackenzie Devilbiss and Chami. And I won't try to pronounce your last name, Chami, I apologize. They will give talks on their research. Mackenzie is a 4th-year PhD candidate. She's from Pennsylvania, Gettysburg, in fact, and she did her undergraduate work at American University in Washington, D.C., before coming to the University of Michigan to work with Professor Myron Campbell on the experiment she'll tell you about today. She's been working and living at Fermilab this year as a Department of Energy Science Research Fellow, and we're very glad that she drove over from Chicago to join us today to give this lecture. Chami will give the second lecture. Chami was also a 4th year. He is also a 4th year doctoral candidate. He's working with Professor Wolfgang Lorentzen on physics underground to detect dark matter. He was an undergraduate at Valparaiso University, but he grew up in Sri Lanka. And I, in fact, met Chami during the summer after his junior year when he was doing a summer research program at Los Alamos. So we're really glad that the 2 of you are here. And Mackenzie, take it away, telling us about shape-shifting the muon to electron conversion experiment.
Thanks for that intro, Tim. Yeah, so hi, I'm Mackenzie, and today I'm going to tell you about the mu to E experiment, which stands for muon to electron conversion. And a conversion, muon to electron, is kind of what it sounds like. A muon is going to turn into an electron without any added other products in this process. So it's almost like the muon is shape-shifting into an electron, which is why I gave the title of my talk today, Shape-Shifting Mystery. So before we get into the meat of my talk, I'll give you a little bit of motivation. So you just heard my name is Mackenzie, and I'm a 4th-year student here at Michigan in my PhD study. But most of you are probably here because you don't really know what a particle physicist does or what questions we try to answer. So hopefully by the end of my talk, you'll have an idea of what we do day to day and what we're trying to achieve as a field. So first I'll start about what is particle physics. I'll give you a short intro about the fundamental questions that we're asking in my field. And then I'll start talking to you about my experiment, mu to E. Why are we looking at muons and why are they so exciting? And then I'll end with what I do day to day and what I've been doing at Fermilab. So what is particle physics? If you just Google particle physics and you read the first sentence of Wikipedia, it'll tell you that particle physics is the branch of physics that studies particles. So that's not very helpful for anybody. Let me give you a more specific intro. So specifically, particle physicists like myself, most particle physicists, are going to be testing our current best model of the universe. And our current best model of the universe is what we call the standard model. So in this diagram here, you can see all of our elementary indivisible particles that we know about in the universe, and this is the entire standard model. So the standard model lists all of our indivisible particles and it describes all of their properties. So it'll describe things like their mass, the charge, the spin of each particle. It'll tell you what type of particle they are. So there are different colors here, or different types of particles. So there are quarks, things that make like protons and neutrons. Then we have our leptons, which is where I'll be focusing. So electrons and muons fit in here. And you have your force-carrying particles. So the standard model tells you about how each of these particles interact with each other. So it tells you about the probability that each of them have to interact with each other and how they interact, the mechanism of interaction. So the standard model tells us a lot about the universe, and we can make a lot of calculations based on all of these rules. So how do we test the standard model? So the standard model I just mentioned, it comes with a big set of rules that govern each of these interactions I just talked about. So when you write down a particle physics process and what a decay actually looks like, usually what particle physicists are writing down and drawing are diagrams like this. So these are called Feynman diagrams. And in these diagrams, each vertex, so where the lines meet, corresponds to a rule in the standard model that you can write down and mathematically work out probabilities for these processes to happen. So these rules are usually about conservation, many of them. So you can think of charge conservation, conserving the charge at the beginning and end of a process, conserving spin. And something that I'm concerned about that I'll get into in a few minutes is conserving something that's called a particle family number. So how we actually test the standard model is that we can think about these rules and we can predict how often each of these processes happen, given these rules that the standard model gives us. So if we predict a certain process to happen, we can look for it to happen and see if that prediction agrees with the standard model, what the standard model gave us for these rules. So that's really how we test the standard model, is we look for mismatches in what the standard model predicts and what we observe in the universe. So now that you know a little bit about the standard model, I'll start talking to you about muons. So what exactly is a muon? So muons fall in the standard model right here beside electrons. And they're beside electrons because they're very similar to electrons. Muons are like heavy electrons. They have many of the same properties, so they're negatively charged, they have the same spin, but they're over 200 times heavier. So they're also fundamental particles, like an electron. You can't break them apart into constituent parts. They're just their own molecule, or their own particle. So here, if you talk about the energy of the particle, E equals mc squared is usually an equation that many people have heard of from particle physics. So this relates energy to the mass of a particle. So if muons have a lot more mass, they're a lot heavier, that means they have more energy, and they have the freedom to decay in many more ways than an electron does. So mu to E, my experiment, is searching for a process that has never been seen, for a muon to convert into an electron without any extra particles produced in this process. So it's not exactly a decay. Usually you talk about particle decays where there are many things produced at the end, but mine really is a conversion because we go from 1 to 1. So it is almost like a shape-shifting of a muon into an electron. There's no other products at the end. So where do we find muons? One of the places that we actually find muons is that they're coming down from the sky all the time. So I have a demo today to actually show you guys this. So this is called a cosmic ray muon telescope, or a cosmic ray muon counter. So if you can hear this, every time this goes off is a cosmic ray passing down from the sky. So how this telescope works is we have 2 detectors, and there are photomultiplier tubes on the end of these detectors. So when a cosmic muon passes down, it'll go straight down through these 2 detectors. And every time you hear this speaker going off with a click, that means that a particle was detected at the same time in both of these detectors. These muons are moving so fast that you really do see them at the same time, even though we have this gap of air between them. And because they're right on top of each other, the only place they can be coming from is from the sky, straight down from the atmosphere. So every time you heard one of these clicks, it's a little bit quiet today, there's not too many muons coming down right now, but that was a cosmic muon coming from the sky. So one thing that I'm going to talk about later in my talk that we might want to know is about a detector's efficiency. So how good are these detectors at actually seeing what we want to detect? So how good is this at seeing cosmic muons? And I did a little back of the envelope calculation last night and calculated that the efficiency of these detectors is we're seeing maybe half of the cosmic ray muons that are actually coming from the sky right now. So you can keep that in mind, and I'll talk about the efficiency of my detectors later. Okay, so now that you knew where muons come from, let's talk a little bit more about the why. So why are we looking at muons? So when muons were discovered, kind of something funny happened. Somebody said, who ordered that? This was a really puzzling molecule or particle to discover. So we knew about electrons, but we weren't sure why this particle was discovered that was so much heavier with the same properties. So that was a kind of funny quip that somebody said when the muon was discovered. So muons have been studied for a very, very long time. I just told you about many of their properties, so we understand them very well. And we also know all of the ways that they can interact with other particles in the standard model and the type of interactions that happen. So if we think about the muon to electron conversion process that my experiment is looking for, we can calculate that rate of probability that it's going to happen according to the standard model using these rules. And the number that we get is that muon to electron conversion happens at a rate of 10 to the negative 53. So that means if you have a decimal point, you put 53 zeros and then a 1, that's going to be the probability of my process to happen in the standard model. So what that means is that if we do see one, that's going to be way outside the standard model prediction. We're going to have a mismatch here. So if we see even a single event, we can ask the question, is a new physics theory a better fit than the standard model to describe the universe? Because we'll see this mismatch in that the standard model might not describe the probability of mu to e that we actually see and observe. So what would that actually mean if we see a rate of mu to e that doesn't fit with the standard model? So new physics theories, these could bring in new particles that would mediate our interaction. So this is the Feynman diagram that you write down if you were going to write down mu to e in the standard model. So you have the nucleus down here, and you have the muon going to an electron at the end. And so if we detect mu to e in my experiment and we find that there's a disagreement with the standard model, our Feynman diagrams might look something more like this, where we could have new particles mediating our process. We also have the potential to discover evidence for supersymmetry, which would introduce a whole slew of new particles to the universe. So this is really why we're studying mu to e. And let's look at, again, a little bit more motivation of why this is so interesting. So I'll go back to these conservation rules right now. So electrons, muons, taus, and neutrinos, those are all of the particles in the standard model that are called leptons. And their interactions, they're generally conserve this number that's called lepton flavor number. So particle family number, a lepton number is one of these numbers. So for a long time in the standard model, we thought that this conservation rule was strictly followed all the time. So if we write down the most probable muon decay, usually when a muon decays, it'll decay into an electron, and then we'll also have these neutrinos produced, a muon neutrino and an electron antineutrino. So if we write down these lepton numbers for this most probable muon decay, you can see that this lepton number is conserved. So you have a lepton number for the muon and a lepton number for the electron species. And on either side of this arrow, you want to balance these numbers. So before and after the arrow here, you have the same number on either side. Whereas let's then look at a muon to electron conversion. So if we write down muon to electron conversion, you have muons going straight to electrons. And you can see here that this lepton family number is mismatched on both sides of the arrow here. So what we call this phenomenon charged lepton flavor violation, and this is actually what I'm looking for evidence of in mu to e. So the reason we're looking for this is we did do experiments in particle physics that observed that the neutral leptons, neutrinos, can directly change flavor. So it really begs us to ask the question, if neutral leptons can change flavor, what's so special about charged leptons? Why are they forbidden? So is the standard model really correct when it's making this assertion? Okay, so now that you know about what we're looking for, why it's so rare, and the motivation behind it, I thought I would talk a little bit more about this 10 to the 53 number, because this is an unfathomably small number. So I tried to think of a comparison that I could do to bring this more down to earth. So do we have anything that is 10 to the 53 on Earth? And I thought of this, so I thought about counting the number of water molecules on Earth. So let's see if we can get close to 10 to the 53 so that you have a sense of how rare a mu to e process actually is. So I started by doing some stoichiometry, and if we start by just counting the molecules in all of the oceans on Earth, we can estimate that we have 4.7 times 10 to the 46. So we have about 6 orders of magnitude lower than where we need to be. So just for fun, let's add in all of the molecules of water in the Great Lakes, in the Greenland's ice cap, and the Antarctic ice cap If you add these, there's still very small parts of water on the Earth, so we still end up with somewhere around 5 times 10 to the 46 molecules of water on all of Earth. And what that means, so we have a 6 order of magnitude difference about. That means if we had 1,000,000 Earths and each molecule of water was a muon, the standard model would predict one of those would be a mu to E conversion process. So this is a very, very rare process according to the standard model. And that's why if we see even one of these, it would be very far outside the standard model's prediction. So if this signal is so rare, how do we even see mu to E if it does happen? So the really special thing about mu to E that I'll talk about as I get more into how my experiment works is that the way we've designed our experiment, the energy of the electron that'll come from a mu to E conversion electron is very high because we stop the muons in a stopping target, which I'll get into later. So this energy is well defined. It's around the energy of the muon's rest mass. And really what this means we need to do is we need to identify all of the other ways that electrons can end up in our detector. And we need to make sure that we know that they're not conversion electrons. So everything that's not a conversion electron, we call these backgrounds. So what this plot is telling you, this plot has a lot of meaning in it, but what I want to point out is these red lines are our signal based on how well we can pick it out. And these blue lines are our background. So you can see here the blue line, if we don't do any sort of selection or rejection to identify all of these non-conversion electrons, the blue line is far above our red line. So it buries our signal underneath all of these backgrounds. And instead, if we can identify all of these other types of electrons that are in our detector solenoid, we can really tune these backgrounds down and get our signal above that blue line so that we can see it above everything else that's happening. So that's our goal, is to identify the conversion electron signal. We really need to reject backgrounds, and we can improve our sensitivity that way. So now that you know about the motivation of mu to E, why we're looking at muons, and why this process is so interesting, let's start talking about how we actually measure mu to E and what my experiment looks like. So then we got the why, and now let's start talking about the where and the how. If you want to look for a muon to do something really, really rare, what you need is to look at a lot of muons. So we need a muon beam, which is perfect to build this experiment at Fermilab. So here's a few pictures of Fermilab. This is the big office building, Wilson Hall. If you're familiar with Fermilab, you've probably seen this iconic building before. But behind Wilson Hall is where the mu to E building is situated. So we have this whole new building that's going to house my experiment. And there's a muon campus back here where there's another muon experiment G-2 running. So the Fermi National Accelerator Laboratory gives us a beam where we can make muons. But the beamline at Fermilab actually produces protons. So we deliver protons to what's called a production target. And these protons are how we make our muons. So when we run protons into this target, which is like a metal block almost, they produce pions. And then these pions decay into muons. So I'm going to show you a demo in a few minutes of how we actually steer our beams and select our muons. But one of the first things, our first line of defense against backgrounds, is that we use a pulsed beam. So our protons are delivered in batches so that when some fast backgrounds happen, they can just decay away really fast before we start looking for a mu to E conversion signal. So to give you an idea of orders of magnitude, we're going to be looking at about 10 to the 20 protons on target through the whole duration of the mu to E experiment. Okay, so I'm going to go through this flow chart a couple times in this talk. So what do we actually need to do to measure mu to E? So this is a schematic of our detectors. So all of our detectors are inside these solenoids, and in a minute I'll tell you why. But we really need to first produce muons and steer them into a beam. So our proton beam comes in here. Here's our production target where we make those pions, and then we steer our beam down through our transport solenoid. So that's how we select our beam. We have our muon beam coming down here. And then I mentioned we stop the muons to get that very high energy electron. So we bring the muons to rest on a stopping target, which is right here. This is our detector solenoid. So this is really where all of the exciting detectors are and where we will look for our conversion electrons. So after our muons are stopped on the stopping target, we want to look for them to convert to electrons. So muons will stop, but electrons will leave. So we watch for these electrons to leave the stopping target, where they will follow in a track through two of our detectors called the tracker and the calorimeter, where we can trace a track all the way through this tracker, and then the calorimeter, we get the final electron's position and energy. And then while we're doing all of these things, we also need to identify everything that's not a conversion electron and make sure we're checking for our backgrounds. Okay, so let's step back for a second and talk about how we steer our muons into a beam. So I have a demo to show you this as well, how we steer charged particles into a beam. So once we have a muon beam, we need to steer it in the correct direction to guide it towards our stopping target. And how we do this is that charged particles, if you put them in a magnetic field, they actually you choose their direction. So here in this demo, we see an electron beam. So I told you electrons are a lot like muons, but muons are heavier. So muons will have a lot more momentum because they have more mass, but this electron beam will act the same way. So you can see this blue beam here coming straight down. I have no electric field or no magnetic field on right now. So our beam is just going whatever direction it wants. So right now I'm going to engage this magnetic field, and you can see that the electron beam will turn, and we can change the strength of this field. You can see it going in a circle now, hopefully. So if I change the strength of this field, we can change the curvature of this path. And by choosing how strong our field is at any given point in our detector, we can really choose what direction our charged particles are going. So this is a really nifty tool that many particle experiments use to select for charged particle beams. So there you go. That's how charged particles act in a beam. Okay, so now that you know how we steer our charged particles and have an idea of how they actually move through this S-shaped solenoid, let me go through this flow chart one more time. So we have our protons coming in here. Oops. Our protons coming in, they hit our production target and we create those pions. Our pions quickly decay to muons. So we have this graded magnetic field here that selects for the correct charge of muon that we'd like, and it also selects for the correct momentum of muon that we'd like. So if that circle is too big, all of these particles run into the wall, and we can select only the interesting muons that we want. So we have this muon beam selection that's happening pretty much all the way through this S-shaped transfer solenoid. And then we stop the muons on the stopping target again. We watch the electrons to eject, we can make their track, and then they're deposited in the calorimeter, and we get their final position and their final energy. So now I'll tell you a little bit about the tracker and the calorimeter. We'll go through 3 of our main detectors in mu to E. So the tracker and the calorimeter are where I will start. This is actually how we track our particles as they move through that big region of our detector solenoid. So the tracker is a lightweight stack of gas-filled straws. I actually have some straw pieces here to show you. So as a particle passes through these straws are filled with gas. And the charged particles will ionize the gas in the straw, and they will create free electrons in these straws. So each of the straws has a very sensitive high voltage wire in the center that attracts these electrons to the straw. And that way we know, based on where these free electrons attract to the straw, where our charged particle passed. We have over 20,000 of these straws in our straw tube tracker, and that way we can get many, many points for where these charged particles pass through our tracker. So I will show you some pieces of the tracker now so that you have an idea of what these straws look like. So our tracker straws are held in this sort of frame, and we have a circular tracker. So here's some of what our straws look like. And we do 3D print this frame ourselves with little holes in it for epoxy. So these straws are basically glued in here with an injected epoxy. And then we have to terminate the straws, and this is where we put on all the electronics. So there are these brass terminations, and we put on these pins to hold the wires. I have some smaller pieces here. So these straws are very, very thin. We 3D print these pieces to hold the wires and the pins as well. You can get an idea for how thin these straws actually are. They're thinner than a pencil. So our tracker has over 20,000 of these straws, and they're arranged in layers. So we have them in 36 different layers, which we call planes. So as our charged particles move through the tracker, we, again, trace this track, so it's exactly what it sounds like, a tracker. And then from where the track, what the track looks like, the curvature of the track, we can get the particle's momentum and the energy of the particle. So the calorimeter is then the next detector that the particle will interact with at the end of our detector solenoid. And the calorimeter are two disks of crystal arrays. So we have almost 1,400 cesium iodide crystals arranged in two disks, front and back. And this will measure the final energy deposition and timing and position of our final state electron at the end of the detector solenoid. So something that's important is that the calorimeter and the tracker can do some of the same calculations, and they can check each other and do independent measurements to make sure that we're really calculating these momentums and energies accurately. So I said I was going to talk to you about 3 detectors, and the tracker and the calorimeter are only 2. There's a third very major detector that we have in Mu-E that is actually the detector I'm working on, and it's called the cosmic ray veto. So this actually deals with those muons from the sky that I told you about at the beginning of my talk. So muons from the sky can fake a signal that looks like a conversion electron. So we really need to have an idea of how often and where cosmic muons are coming into our detector solenoid. And how we do that is we have this active shield called the cosmic ray veto that can detect and then reject cosmic muons. So our cosmic ray veto covers pretty much the entire detector solenoid and then a little bit of the transport solenoid. So if I showed it to you before now in the talk, you wouldn't have been able to see all this fancy technology we have underneath. So just to give you an idea, this dashed box is about where the CRV covers. So it'll just cover almost everything I told you about so far. So the cosmic ray veto is a very important detector because cosmic rays are actually Mu-E's most dangerous background. So if we did not have this detector, we would get 1 fake conversion electron signal every single day that would be from a cosmic. So what we do to mitigate against this background is we have scintillating bars that are arranged in 4 layers, over 5,500 scintillating bars, and I have one of those here to show you as well, that I'll show you in a minute. But we arrange them in 4 layers and stagger them so that anytime a cosmic muon passes, no matter what sort of trajectory it takes through the sky, it hopefully won't pass through a gap, and we can detect anything that comes through above or to the sides of this detector solenoid. So we need a really, really high efficiency for this detector to reject all of these cosmic muons. And our goal here, or our requirement, is 99.99% efficiency. So over 1,000 days of running time, we don't want to see a single fake cosmic that can create a conversion signal. So I'll show you what I'll show you what a scintillating bar looks like now from the CRV. Get my tracker pieces out of the way. So here's what a Mu-E scintillator bar actually looks like. Scintillators are plastic. So when a particle would pass through here, it creates light. And then these fibers are actually, we don't have the fiber inside, but they will be epoxied inside, and the fibers are actually what will send the signal to electronics on the outside of the CRV to tell us exactly when and where cosmics pass through this active shield. And we have like 2 of these bars for each counter, and then we stack them in layers of 4. So there's a piece of the CRV. And so what it actually looks like when a cosmic ray passes through this detector is we look for a sort of coincidence, similar to we look for this 2-fold coincidence in the cosmic ray telescope that I demoed for you. In the cosmic ray veto that I use in Mu-E, we require a cosmic ray to be detected in at least 3 of the 4 layers. So our cosmic ray telescope over here counted muons when it detected in 2 layers. We require at least 3 to make a detection. So if a cosmic muon comes down through the cosmic ray veto, we will detect it in these layers, potentially up to 4 layers. And if we do see it in at least 3 of the 4, we call the signal a CRV stub. And we say that means a cosmic ray passed at this time. And what we actually do is we say there's a length of time that we don't know whether or not it could be a fake conversion electron signal. So we reject that data, and we just don't analyze that for a certain period of time, short amount of time. So, okay, let's go through this flow one last time for what we actually detect from particles in the detector solenoid and how we evaluate whether or not it's a good candidate for a conversion electron. So the first thing that we need to know about is the particle's origin. So I've made a big deal about knowing whether or not the particle comes from the sky or from our beam. So if the particle comes from the beam, it'll be ejected from the stopping target, and we have a way to decide in our code whether or not that happened. But if it's from a cosmic ray, we'll see that CRV stub, and we'll say, don't analyze this data. This could be a fake cosmic signal. So, okay, if we don't see a cosmic ray, then we move on to analyzing whether or not we have a conversion electron signal. So it comes from the stopping target, then the particle will enter the region of the tracker, where we make that track and we track its path. So from that path, we can get the particle's momentum and compare that to what we expect for a conversion electron. Then the particle will land in the calorimeter disk, where we get the calorimeter cluster of its final energy and position. So we can compare that final energy to what we expect for a conversion electron as well. So with a handle on these three things, following the particle through our detector solenoid, we should be able to get a good handle on whether or not this is a conversion electron or some other background process. Okay, so that's basically the big picture of mu-to-E. Now I'll zoom you in on what actually I've been doing at Fermilab. So here's a few pictures of me when I arrived at the lab. I just got there in January, so I've been working there for a few months now. But I've actually been working on testing cosmic ray veto modules, so these CRV modules that I just talked about. And my goal at the end of my time at Fermilab, so I'll be there for the entire year this year, is to estimate the efficiency of the CRV and make sure we are at that 99.99% level. So we want to know how well it will work before we put it together. mu-to-E is still under construction. We're not actually taking data yet, so it's really important to check all of our boxes before we turn our experiment on. So how do we actually determine the CRV efficiency? We want to know if, again, efficiency is how well the detector will do. So if we have detectors that we make the CRV detectors ourselves, so we need to determine how efficient they are. And how we do that is we want to know really the number of particles that we detect over the number of particles that actually pass through. So if we detect everything that passes through, you're 100% efficient. For instance, if you send 100 particles through and you see all 100, you're great, 100%. If you miss 3, that means you're 97% efficient in this case. So how I'm actually looking for this is we take 3 CRV modules and we stack them on top of each other. So what you look for is we say, if particles went through the 2 outer counters on the top and the bottom, they must have also gone through that middle counter, right? So this is how I'm calculating efficiency. I compare the rate that we see in the outside with the rate that we see in all 3. So if it goes through all 3, it also went through the middle. And then that ratio is what I'm determining to be the efficiency of our counters. And with the efficiency of one counter, we can extend to the efficiency of the entire cosmic ray veto. So that's my goal for the year, is how many does the cosmic ray veto actually see? And are we at this 99.99% level? So how we get 99.99% is, right, we have one fake cosmic every day if we don't mitigate this background. mu-to-E's running time when we do turn on will be about 1,000 days. So if we want to see no signals over 1,000 days that are these fake signals, we need this efficiency of over 99.99%, which is greater than 1 over 1,000. So if we don't get this efficiency, we're really at a danger of seeing these fake conversion electrons from cosmics. So my job is pretty important this year. So to wrap up my talk, mu-to-E is being built at Fermilab. We should turn on probably in 2025 or 2026, but we're still under construction right now. We're looking for evidence of charge lepton flavor violations. That's really the mechanism we're looking for in the standard model that could introduce a lot of new physics to the universe if we do see evidence. So there are hundreds of physicists working on mu-to-E. This is a picture of some of them from an older collaboration meeting, and this is a picture of the Mu-to-E Hall. So when Mu-to-E is built, it will go in this big hole, and then it'll be covered with the cosmic ray veto, and then with concrete, because things will get radioactive. But this is an exciting place to be. So I think finally, measuring properties of our detectors, like the efficiency that I'm working toward, is a really important part to get us to where our experiment needs to be when we do start collecting data. And just to remind you, we're searching for this 10 to the 53 rate. So we want to get our experiment as sensitive as possible. In the end, when we do finish constructing mu-to-E, it will be over 1,000 times more sensitive than any experiment has ever been before that searches for this conversion process. And if we do see mu-to-E, we have the potential to discover new physics. So definitely keep on the lookout. And with that, I think I'll pass it over to Chami.
Thanks, Mackenzie. That was great.
Thanks.
We're moving to Chami now. While he gets set up, I want to remind you that you can ask questions that we will present to the speakers after Chami's talk. We have cards here for those in the audience, and people at home can email us questions at physics@umich.edu. So Chami is going to tell us about the quest, the underground quest for dark matter.
Hi everyone, my name is Chamindu Amarasinghe, and we're going to be talking today about the underground quest for dark matter. But first, let's travel back in time a little bit to the ancient world, which witnessed the birth of astronomy. And this is where you'd look at the night sky and try to come up with rational explanations of the celestial phenomenon that you'd observe in the universe. Over time, for example, with the invention of the telescope, you'd be able to see stars and moons and planets that had previously been too far away or too dim for us to notice with our naked eyes. When you look at these objects, you often discover deep scientific principles about the universe, like Newton's law of gravity, which tells us how objects with mass are attracted to each other. Scientific principles like this are kind of powerful because they allow us to make predictions about objects and phenomenon that we have not discovered yet. For example, based on the understanding of gravity at that time, in 1846, astronomers were studying the orbit of Uranus, and they noticed that this planet appeared to speed up and slow down depending on where it was in its orbit. And it was as if an undiscovered planet was tugging at it. And so Neptune was discovered. When we don't see what we expect from these scientific principles, something interesting can also happen. In the last edition of Saturday Morning Physics, Professor Pandazayas talked about the anomalies in the orbit of Mercury. And in 1859, astronomers hypothesized that there was an additional planet called Vulcan that was inside the orbit of Mercury that was causing these anomalies. In this case, however, it turned out to not be the case. There is no planet Vulcan. And the explanation for the anomalies in Mercury's orbit had to wait until the next century when Einstein's theory of general relativity came out. So the story of dark matter is kind of similar, and it's at a crossroads right now. There are many observations in our universe that can only be explained if the universe contains large amounts of unseen matter, and this is what I'll be talking about today, or it could be that our current theory of gravity needs to be updated. So dark matter is an invisible substance. It's invisible to even our most sophisticated instruments. How do we know that it exists? There are several types of evidence. For example, scientists who are studying the evolution of galaxies noticed that they wouldn't have formed the way they did if there weren't large amounts of unseen matter to bind them together. Another line of evidence comes from gravitational lensing, in which light from distant objects appear to bend around large amounts of matter when reaching the Earth. But we don't see this large amount of matter. The cosmic microwave background radiation is also another very important line of evidence. It is basically a cosmic archaeological record of the early universe, and it provides very strong evidence for the existence of dark matter. But the simplest type of evidence, and this is the type that came up first historically, is the observation that astronomical objects move under gravity as if they're heavier than they look. This type of evidence first came up in the 1970s when astronomers were looking at the motion of galaxies, like this one pictured here. Now, galaxies are made up of stars and dust and planets. And if you assume that all of the mass in the galaxies are due to those visible components only, you can use our understanding of gravity to figure out how they should rotate. And this is how such a galaxy should rotate if all the mass is contained only in its stars and dust and gas. But when we look out and actually make measurements of these rotating galaxies, we see something closer to the right, where they're moving much faster. And one of the explanations for this is there's large amounts of unseen matter that's causing these stars to rotate more quickly because of the additional gravitational forces. Okay, so we know quite a lot about, well, we know some things about dark matter. We don't know everything yet. And some of these things are, we know that in the observable universe, dark matter has to weigh 5 times as much as regular matter. One other thing we know that it has to be very stable enough to influence the formation of large-scale structures in our universe. And we also know that it barely interacts with standard matter. For if it did, we would have seen it already. Now, usually when scientists see something unexpected like this, there are often clear lines of investigation that we take to figure out the mystery. For example, in 1846, when people were looking at the orbit of Uranus, this scientist wrote a letter to the Berlin Observatory and said, "I've done some math and I've looked at the orbit of Uranus, and I expect this new planet to be discovered right at this exact position in the sky. Can you please look for it?" The very same day that the Berlin Observatory got this letter, they pointed their telescope in the exact location where this scientist predicted the planet and discovered Neptune. This is not the case for dark matter. We know very little about what it is. For example, we don't know what an individual particle of dark matter could weigh. Modern searches look for particles that are lighter than a neutrino, which is the lightest massive particle that we know of, all the way up to particles several times the mass of our sun. This is an incredible range of masses, and we've not discovered it yet. A physicist at NYU once likened the scenario to pre-modern scientists understanding the concepts of buoyancy and pressure, but without knowing that the chemical formula for water is H2O. In this talk, I'm going to be talking about WIMPs, or weakly interacting massive particles. Okay. So how exactly do we go about detecting dark matter? Scientists who study this look at every conceivable front, from using detectors that are deep underground to space telescopes. And there are 3 main methods in which we go about this search. The first is indirect detection, where we look for signatures of dark matter particles interacting in space. And you can look at this diagram, and indirect detection is the arrow pointing up, where you look at 2 dark matter particles interacting in some distant galaxy and producing some normal matter, like light, that we could pick up using our space telescopes. The second way to look for dark matter is to start with normal matter, so this is the arrow pointing down. We collide this normal matter at extremely high energies at our particle accelerators with the hopes that they create some dark matter we can detect. The third way is direct detection, and this is what I'll be talking about. In this case, we're looking for dark matter particles passing through the Earth and interacting with our terrestrial detectors. So dark matter passing through the Earth, interacting with normal matter, and we're looking for some signature in the normal matter. Okay, so let me point your attention to a direct detection experiment that's happening in the town of Lead, South Dakota. This place used to be the home of one of the most productive gold mines in the world. But since then, they've turned from mining gold to science. Now, surf has already been the site of a major scientific discovery in the 1960s when measurements were made of the solar neutrino flux passing through the Earth. Since then, attention has shifted to dark matter searches. And from 2013 to 2016, the Large Underground Xenon Experiment, or LUX, looked for dark matter. They didn't find anything, but it told us exactly how weak dark matter should interact. Now, LUX Zeppelin or LZ, is the experiment that I'm working on, and it's a successor to LUX. It's located in the same cavern. The Earth beneath LEAD is riddled with a lot of tunnels. But this picture just shows the main science level where we have our experiment. It's a mile underground, and it's located in this place called the Davis Cavern, which hosted the solar neutrino experiment and LUX, and is currently hosting LZ. Just for fun, I've included a picture of Ray Davis Jr., who was one of the pioneers of the neutrino science that happened in the 1960s, taking a dip in the water tank underground. I haven't tried this, but I'm pretty sure we're not allowed to do this today. All right, so why do we go underground? LZ is a low background experiment. And what this means is, since WIMPs hardly interact with normal matter, we expect only a few WIMP events per year. So we require very precise accounting of all the other types of interactions that could occur in our detector, and these are called background events. So the less background events there are, the more easy it is for us to do this accounting. Cosmic rays, that Mackenzie talked about in her talk, are a significant source of background for her experiment as well as ours. They happen to have a very high flux at the Earth's surface, and they're produced by high-energy particles, usually protons, that interact with particles in our atmosphere and create large showers of particles. Some of these particles are muons, and we heard examples of them using the muon counter today. It turns out that rock is a pretty good shielder of muons. So we go underground to escape the background from the muons. In this setup here, I hope to demonstrate the importance of having a low background experiment when we're looking for a rare and faint signal. So to simulate the background, there's a white noise generator here that I'm going to turn on. Okay, so this is supposed to be, we're at the surface of the Earth, and this is our muons. We can hear it. To simulate the dark matter, I'm going to be dropping a pin. Now, unless you have exceptional hearing, I'm pretty sure we're not going to hear this. So let me try it once. Okay, maybe some of you heard it. Let's pretend we didn't. Okay, I'm going to turn on the spectrum analyzer here. This is basically a plot of the frequencies that we're hearing, that the microphone is picking up. So when we go underground, we reduce the background, and when you drop the pin, hopefully you can hear it now. So I'm going to reduce this to very low levels, and you should be able to hear it, and hopefully you should be able to see the several bands of frequencies crop up on the spectrum analyzer. Now, in case you aren't convinced, or if you didn't hear the pin, I also have a different source of our WIMP signal here, which is a function generator. It produces a constant beeping noise. So I'm going to turn our background back up, and you can see the spectrum is back at white noise. And now I'm going to turn the function generator on. Okay, I can't hear anything, but let's go underground now and reduce the muon flux. And keep an eye on the screen as I reduce the background. And there's the WIMP signal, pretty clear. Okay, turn these off. In fact, when we go underground, the number of muons that we see reduces by a factor of 1,000,000 when you get down to the level of LZ from the surface. Okay, so some colleagues of mine who play Minecraft have created a virtual universe. And this is meant to illustrate our commute when we're out there working on site in South Dakota. So we show up bright and early, and we enter the building where we have to put on our safety gear. And this includes boots, coveralls, hard hats, air purifying respirators in case of an emergency. So you put all these safety gear on, and you walk through several dark tunnels until you get to the elevator, which takes you 4,000 850 feet underground. There's the elevator. We call it the cage. The cage ride is around 12 minutes. It's dark, it's jerky, and it's often wet. If you're unlucky on a crowded day, you'll be stuck with a constant drip of water on your head for the entire cage ride. Now, the cage is our lifeline. It provides everything we need to build and to operate the detector, including supplies, equipment, and of course, a daily supply of personnel. So we're on the Davis Cavern now, which is the science level, a mile underground. And here we have to be careful to clean our boots and take off the dusty mine clothing, which the dust is very bad for the experiment. It can be radioactive and interfere with the measurement. So here we take off our boots and we enter what looks like a maze of clean rooms where we successively put on clean shoes, clean clothes, clean hard hats and goggles. And after we go through this maze, we will emerge into the Davis Cavern where the science happens. And here we are. This is a poster of LZ, which actually is not real. It just happens in Minecraft. This is the upper floor of the Davis Cavern, which hosts our electronic systems and cryogenic systems. And it also has the control room where we hang out and have meetings and monitor the detector. Now downstairs is where the detector is. This is what you see. This is a big gray blob. But unfortunately, LZ Minecraft is not detailed enough to explore this fully, so we're going to take a closer look at that. Here's some pictures. Donned our safety gear and moving equipment underground. This is what the upper Davis looks like. And here are some friends from U of M involved in commissioning the water tank. Okay, so this is what the LZ detector looks like. My friend Maurice likes to say that it looks like a Russian doll because it's detector inside of detector inside of detector. Now, the most important piece of this is the central volume. It contains 7 tons of the liquefied noble gas xenon, and it's kept at a frigid minus 100 degrees Celsius. Outside of it, you can see the outer detectors, which are instrumental in reducing the background that we have in LZ. All of this is submerged in about 220 tons of water in the water tank. Okay, so this central volume, we call it the time projection chamber. And it's filled nearly to the top with liquid xenon. And there are 2 arrays of photomultiplier tubes, one on the top and one on the bottom. These photomultiplier tubes, or PMTs, are extremely sensitive light sensors. The ones that LZ uses are capable of detecting single photons. In addition to this, there is a strong electric field in this region that points downwards, and it's very important to the function of this detector. So how does it work? When a particle enters the TPC, hopefully a WIMP, and interacts with the liquid xenon, there are 2 things that happen. Firstly, there's an initial flash of light. This is due to a property of xenon called scintillation. The scintillation light from xenon is pretty characteristic. It has a wavelength of about 175 nanometers, and it's picked up by the PMTs. We call this primary signal the S1. At the same time, another thing happens. At the site of the interaction, a few electrons are knocked loose from the xenon. In the electric field, these electrons are drifted up and extracted into the gaseous region. These extracted electrons then cause the gaseous xenon to scintillate. This produces a secondary signal, and we call that the S2. The S1 and the S2 are the main signals that we look for to identify interactions in LZ. Okay, so why liquid xenon? It's an attractive medium for dark matter detectors for several reasons. Firstly, it's pretty dense. It's about 3 times as dense as water, which means you can put a reasonable amount of it, a large amount of it in a reasonable amount of space. This is important because since WIMPs interact very rarely with regular matter, having a larger detector increases the chances of seeing a potential interaction. Having a large detector is also important because of the phenomenon called self-shielding. The xenon at the outer edge of the detector blocks a lot of the radiation coming from external sources. And so this allows for a very quiet inner volume. This plot shows the position of the backgrounds, and you can see that they're mostly located around the walls of the detector. Natural xenon also has no long-lived radioactive isotopes, so we don't have to worry about internal contributions to the background. Xenon also produces S1 and S2 signals in response to very low energy deposits. And this helps us when we're looking for light WIMPs, which deposit less energy in our detector than their heavier counterparts. But I'd say one of the most important properties of liquid xenon is that using the S1 and S2 signals, you can tell whether the particle that came in and interacted with the xenon did so with its nucleus or with its orbiting atomic electrons. So let's take a closer look at that. WIMPs, like neutrons and neutrinos, are electrically neutral. So they're able to pass through the electron cloud of the xenon and interact with the nucleus. Gamma rays and beta particles, on the other hand, that come from the radioactive decay of materials, interact with the atomic electrons. These two types of interactions are called nuclear recoils and electron recoils. And they affect the scintillation process in liquid xenon. So they affect the relative sizes of the S1 and the S2. In this figure here, I've plotted the size of the S2 signal on the vertical axis and the size of the S1 signal on the horizontal axis. And I've shown some examples of electron recoils in blue and nuclear recoils in orange. And you can see that they're separated from each other. This is important because the signal that we expect, the WIMP, is a nuclear recoil, but a lot of our background in LZ are electron recoils. So this separation helps us because we can, if you just look at this area, we know that we only will expect WIMPs there. Understanding backgrounds is probably the most important thing when running a detector such as this. So we've identified several sources of backgrounds, both electron recoils and nuclear recoils. And these can come from several parts. They can come from the radioactive detector components and surfaces. They can come from contaminants that are dissolved in the xenon. They can come from external radiation from the laboratory. Or they could be what we call physics backgrounds, which are mostly neutrinos coming from outer space. I think it's interesting that in the olden days of underground science, the only signal that people were really interested in were the neutrinos. But in modern day dark matter searches, they are a pesky background. In this plot, I've shown the frequency of nuclear recoil backgrounds on the vertical axis, plotted against the energy that they deposit in our detector. And I've shown in this blue band here, the energy region in which we expect a WIMP. This is a very similar plot, but for the electron recoils. I'm not going to go into detail into these plots, except to point your attention to the dominant contribution in the WIMP region, which is radon 222 over here. We have to do our accounting really, really carefully. At the end of the 1,000-day observing period of LZ, once everything is, all the data is collected and analyzed, and we look into the specific region of S1, S2 space in which we expect our signal, we only expect 6 background events. Around 5 of them are ERs, and the other one is an NR. So that's extremely low background, and that's how precise we have to be in our experiment. So, I mentioned that radon is a big problem. In fact, I would argue that it's one of LZ's biggest problems because it's continuously emanated from the decays of uranium and thorium in parts of the detector, and radon readily dissolves in liquid xenon, where it decays further and creates electron recoil backgrounds. So to mitigate this, LZ uses an inline radon reduction system that was developed, tested, and deployed by the University of Michigan. And this is the basic principle of what it does. It pulls gaseous xenon out of the TPC, puts it into the radon reduction system where some of the radon is removed, and we return clean xenon back into the TPC. How does it work? Well, it works by, when you put a mixture of gases through a series of filters, these filters these filters trap the radon atoms and let the xenon atoms through. This works because radon is a much bigger and heavier atom than xenon. So the relative speed of radon is much slower than xenon. So this is what the LZ radon reduction system looks like in this diagram. It's basically a series of 4 columns that we fill with an adsorbent material that we have to choose with some considerations in mind. This material has to have a very large surface area per mass because we want to trap as many radon atoms as possible onto the surface. Secondly, it has to have appropriately sized pores so that the larger radon atoms get trapped, but the smaller xenon atoms are let through. And finally, it has to have an extremely low intrinsic radioactivity because we don't want our radon reduction system to introduce more backgrounds than it takes out. Okay, so it turns out a good candidate for this material is charcoal, which I was initially surprised by, because I would imagine charcoal is pretty dirty. But it turns out you can make very clean charcoal. And at the University of Michigan, we've tested several different types of charcoal, Saratech, Carboact, and the Shirasagi, and we've decided that the Saratech has the properties that we want. Now, I wish I could show you a jar of dark matter, but that's impossible, so I got the next best thing, which is a jar of the charcoal that we use. So it's actually pretty fun to play with. It's made up of little beads, and you can like pour it from one beaker to the other. I actually put some in a little dish, and hopefully you can see what it looks like. It's almost like a fluid. But this charcoal has exactly the properties that we want. It's got a very large surface area, and it's got a pretty low activity, so it's not very radioactive. And it also doesn't break the bank, unlike Carboact here, which costs $15,000 per kilogram. Okay, so in the winter of 2020, we packed up the radon reduction system that we've been working on at Michigan and shipped it to SURF, where after extensive testing and leak checking and assembling, we packed it up to send it underground. This is actually a very nerve-wracking time for the U of M team at Michigan because we were very worried that something could go wrong, something could break during the transportation process. But everything worked out fine, and after some final leak checks and further tests underground, it was installed, where currently it is happily chugging along, removing radon from LZ. Okay, so LZ is currently taking data underground, and we are actively analyzing it as I speak. And it'll take some time for us to reach some conclusions about dark matter. But even before we built the experiment, we made pretty precise calculations about how much background we expect. And therefore, we can make a statement about how sensitive LZ will be to dark matter interactions. So if you look at this plot, I want you to read the vertical axis as the strength of the WIMP interaction. So upwards means stronger WIMP interaction, and downward means weaker WIMP interaction. And this is plotted against the mass of the WIMP. The black line here shows the weakest interaction that LZ will be able to observe after 1,000 days of data collection. So this means that if dark matter interacts with a strength that's above this black line, then we will discover it. Now, previous experiments like Lux and Panda X and Xenon 1 ton have looked, and they've created this series of lines, and they've basically said, well, we didn't find anything, so if dark matter exists, it cannot be above these lines, it has to be below these lines. And that's exactly the region that LZ will look at. It also means that if we don't discover dark matter, which is likely, we'll be able to exclude this region of parameter space, and we'll be able to say that if dark matter exists, or if WIMPs exist, they must interact with a string that's below this line. Now, future experiments like this one will be bigger and better and more sensitive. But there's a fundamental limit to this with using this technology. It turns out that there's an irreducible background from neutrinos from outer space that will not allow us to be sensitive to dark matter anymore. And this is the region that's in orange right here. Once future experiments reach this level, we won't be able to tell if a particular event is due to a WIMP or due to a neutrino. But we're not there yet. Okay, so the outlook is dark, quiet, and it's underground. These happen to be perfect conditions for WIMP hunting. And LZ is currently running the world's most sensitive search for these particles. Ultimately, only time will tell if we make a discovery or not. At this point, I'd like to thank my collaborators from LZ. We are a collaboration of 36 institutions and more than 250 scientists, engineers, and technicians. And we're supported by these organizations. There are numerous WIMP hunters at Michigan. And here are some of them. I see some of them in the audience today. So I'd like to thank you all, and thank you for listening. Yeah.
Thank you, Chami, for a second excellent talk here today. So we will move to a question and answer period. If you here in the audience have written questions for either of our speakers today on your cards, Professor Clark will collect them. I think what we should do is we will start with questions for Mackenzie and then go to questions for Chami. I think there's another microphone, or for you, or you both have. Okay, great, that'll work. Then we have some questions for both of you. Okay. So Mackenzie, are you ready?
Yeah,
this
I'm
may
ready.
be so these are really interesting questions. First one is, why the standard model is so small, and why is something so small not actually zero, right? Is there?
Yeah. So, well, okay. So yeah, this is an interesting question. So measuring something to be zero and expecting something to be zero are two completely different measurements. So if you expect something to be very, very small, like mu to e, it does happen. It's not that the rate is zero. Like, these processes will happen. But kind of like Chami's experiment, how you have this parameter space where the strength might be below that line, that's sort of how mu to e is right now, is where our sensitivity is as best as we can do, but this mu to e conversion process might happen below the parameter space that we're able to see. So we still might see zero, but that doesn't mean mu to e doesn't happen. It just means it's much more rare than our experiment has the power to see.
Okay, that's cool. It's a little bit expert. So you said that the muon is negatively charged, but there are positively charged muons.
Right.
Are you actually measuring both of those, or are you measuring only the negative or only the positive muons in your experiment?
My experiment has some power to do some positive muon searches, but the way that we configure our magnetic field in the gradient and how we steer our muon beam, we do select for the negative muons to come down our beam line. So we don't actually stop any positive muons. Those actually will travel the opposite way and will run into the wall of our detectors. So I guess instead of looking at mu pluses, which is what we usually call the positive muons, we still look at mu minuses, but we do have some sensitivity to look for like a mu minus to an E plus channel, because there can be some charge switching around as well. So we don't actually look at the positive muons. Those are selected out of our beam line.
I see. Let's see, there's another question here. I should say that the audience is extremely complimentary and thinks that you've both given great talks and have wonderful futures. So I want to pull that out of these. So even if your muon veto achieves, I guess it's 99.9%, so that's only 10 to the minus 4.
Right, yes.
There must be a lot of factors to get to 10 to the minus 18.
Yes. Yeah, the factors that we use to get to 10 to the minus 18, right, the cosmic ray veto gives us a rejection power of 10 to the minus 4 against our cosmic ray background specifically. But the other ways that we design our detectors, so for instance, we have this S shape of our solenoids, whereas you might think, why do you have that S shape? You could just send a muon beam, straight into your detector solenoid. So things like that S shape allow us to control for some background. So I've mentioned like tuning, if we have, a low energy muon coming down the beam line, you can tune that with the magnetic background. That low energy muon that might not be exciting could run into the wall. It doesn't have to stop in the stopping target. So we have a lot of knobs on the way to detecting the final state electron where we reject other kinds of backgrounds. The cosmic ray veto is only one of these ways. We also look for things like, do we actually have no particles in between our batches of protons that we send? So we look for an extinction factor. We make sure nothing is happening really in that dead space of time where we expect nothing to happen. So we have a lot of checks and balances that we do on the way that have go beyond cosmic ray veto mitigation.
Okay, cool. I should note that our Saturday morning physics audience is very sophisticated. So here are a couple of interesting questions that are somewhat related. So one is, do the muons come continuously, or do they come in pulses, I guess?
Yeah, so that's a little bit, they do come in pulses because we pulse the proton beam, but you can imagine you have some time that it takes for these muons to decay. So the proton to pion to muon chain takes a little bit of time for the muons to be produced. So they do travel down the beam line. They can be spread out from these batches a little bit, but we do still have this dead space in the middle that we do look for zero particles to be there. So we look for this dead space in between our batches. So we space the protons, the muons get a little bit more spread out, but we still have space between those batches, yes.
One of our listeners notes that the 2 microsecond the lifetime of the muons when they're stopped.
Yes.
That kind of is what smooths it out.
Yeah.
Spreads it out.
Yeah, exactly. So our detection window is actually, almost 2 microseconds. We look at a few thousand nanoseconds for our detection window. And some of that is that dead time that I talked about. So we only look at a small fraction of that time for where we look for conversion electrons to be produced.
Yep. I guess this question, there's a couple of questions here that go back to the positive versus negative muons.
Okay.
And maybe also, I saw positrons and electrons mentioned as well.
Okay.
So they must be produced, and of course when the muon decays, they're produced. And then they, if there's antimatter, so like positrons, they must annihilate somewhere. Is that a problem? I guess that's how I will try to paraphrase these questions.
Yeah, so, right. Anything that you can think of that is not a mu to E conversion on that stopping target nucleus can happen and is a background. So we are looking for this very rare signal, and we need to have a good handle on everything else. So we do have annihilations that occur, and annihilations usually, like an electron and a positron annihilation results in like final state photons. So we detect light, and we can really get the energy of that light and say that it came from an annihilation. And those also, so a lot of other processes that produce these background electrons that I've been talking about, those electrons are much lower in energy than our conversion electron. So we stop the muons on our target, and when you bring a muon to rest, that MC squared, it has no C component. So its energy is just the rest mass. And when we have the conversion electron come out from that rest mass, it takes almost all of that energy with it. So you have an electron moving with basically the energy of a rest mass muon. Usually when we have these other background processes that happen from our beamline or from like other processes that can happen, the energy of the electrons they produce is much, much lower because they're not having all of that energy from the muon's rest mass. They're muons that could be moving, You could be coming from particles that aren't muons. You could be coming from an annihilation of electrons, which have much lower energy to begin with. So a lot of the other stuff we detect that's much lower energy falls on a lower energy scale that we're not even looking at for our final states. I hope that helps. It's not too technical.
Okay, great. Did we get any cards? Not yet. Okay. Any other cards, I should say. All right, great. Thank you, Mackenzie. So I have some questions for Chami now, and then there is at least one question for both of you. All right, so the first set of questions are, in fact, about the general nature of dark matter, I guess. Is there dark matter between galaxies? So you showed us this effect of dark matter on galaxies, stars and galaxies.
Yeah. So I mentioned one of the primary pieces of evidence for dark matter came from the rotations of galaxies. That was in the 1970s. But back in the 1930s, people were looking at the motion of clusters of galaxies in which there were, several hundred galaxies together bound gravitationally. And they found the same thing, that they were moving as if there were large amounts of unseen matter between them. So yeah, there are lots of dark matter between galaxies.
Okay, and related, maybe. Could there be more than one kind of dark matter that's doing all of this?
Absolutely. There's no reason that dark matter is a WIMP and is only a WIMP. We just don't know. There could be several different types of dark matter that each have different masses. Since we only know the bulk properties of dark matter, like the average energy density in the universe. But other than that, we really have no idea as to what the particulate nature of it is. And it could be several particles.
I have to admit, so I've been wondering if, since there are several signals, so the cosmic background radiation, galactic rotation, galactic cluster rotation, and others you mentioned, does that sort of bigger picture constrain what dark matter could be in any way?
Yeah, so all of these pieces of evidence fold together to make what's known as the lambda CDM model of cosmology, which stands for lambda cold dark matter. So all of these pieces are consistent with this framework, and it tells us certain things like what the dark matter content of the universe is. So for example, I mentioned the energy density, the average energy density of dark matter. It tells us what that is. What's interesting is I mentioned that there's this other explanation for these observations, which could be maybe some modification to our understanding of gravity. And there the evidence does not point to that as much. So there is more evidence that points to the existence of dark matter in this particular framework than there is evidence that points to this modified nature of gravity. I hope that answered the question.
Yeah, that is certainly in the direction.
Okay.
Great. There's some technical questions here. Is xenon expensive?
Yes.
Interesting question. And where does it come from?
Someone asked me this question before the talk started, and honestly, I'd forgotten. And then I asked my advisor, Wolfgang, who said that xenon is very expensive. Right now, it costs about $10,000 per kilogram. So the total mass of xenon in LZ costs around $30 million after all the work we put into to purify it. And I think xenon comes from the atmosphere where we extract it.
Okay. Is xenon expensive? Where does it come from? Back to WIMPs, actually. Could they be charged?
WIMPs are not charged, but there are other, perhaps more exotic models of dark matter in which you can have charged particles. An interesting piece of research that I was reading about a few weeks ago talked about macroscopic dark matter, which could be charged. And the way that these people were looking for signatures of this dark matter was they were looking for the dark matter to tear through the atmosphere and leave a trail of ionizing radiation. which, if it occurs in appropriate conditions, would result in straight lightning instead of jagged lightning. So they use the non-observation of straight lightning to set limits on this type of macroscopic dark matter. So yes, there are models of dark matter that are charged.
Clever. So it might be easier to detect if it were charged, but also harder because you wouldn't be able to go underground.
Yeah, yeah.
Okay, let's see. So is there any disadvantage to putting this experiment underground? Are you making compromises?
Yeah, one of the biggest compromises, at least at SURF, is we are limited by the size of the mine shaft. We cannot build anything that has components that are larger than the size of the cage because we have to bring it underground. So that's one of the main reasons we haven't built a bigger LZ, because we just can't fit the parts underground. One of our competitor experiments is called Xenon Anton, and they're also very similar to LZ. They have large amounts of rock above them. The difference there is that they're located at the base of a mountain, Gran Sasso in Italy. So to get to their lab, you essentially drive into the mountain, and they have no restrictions on, no big restrictions on the size of the things that they can bring in.
Cool. So there was interest in your radon reduction system and also other things that may be purified because you're circulating the xenon, right? So are there other things that you remove or that you're removing from the xenon?
Yeah, so before the xenon made its way underground in South Dakota, all tens of tons of it was purified to remove the element krypton from it. And this was done in the Stanford Linear Accelerator Complex in Stanford. So that's a purification that's been done before the xenon was put into place. But yeah, we are actively circulating the xenon while LZ is running to remove radon and to remove other contaminants in the detector. Yeah.
Is your charcoal also radioactively special? So in particular, carbon-14 is part of all charcoal, right? I wonder if that's a problem.
I'm not sure. Maybe Wolfgang or Maurice. It's
not a problem because it's a beta emitter. Is that the reason? Okay. So the answer for people at home is that it's far away from the detector, really, this purifier. So the carbon-14 shouldn't be an issue. Okay, thanks. There's a question about this neutrino signal that's your sort of ultimate limit. Why is that signal not different from a WIMP signal? Neutrinos are different, right?
Yes. So this particular signal occurs in an interaction in which the neutrino, which is electrically neutral also, like a WIMP, it passes through the electron cloud of the xenon and interacts as a whole with the xenon nucleus. And this is called coherent neutrino scattering. And it produces exactly the same type of signal as a WIMP would, because a WIMP also interacts with the nucleus. Yeah.
Okay, cool. And then there's somebody who's concerned for your safety. Are there stairs?
Are there stairs?
Are there stairs to get up from the?
No, there are no stairs. There are two shafts though. So in case, they really thought very carefully about the safety. We have the primary shaft, which is the Yates shaft, it's called, that we go down every day. But there's also, in case if something happens, if the cage gets stuck, as it does once every few weeks, and we can't go up, or if there's inclement weather, then there's a secondary shaft in which we can escape the mine.
Not sure this is a kind of science I could do. All right, so there's actually another muon question has come in, and then we have a question for both of you. So let me just this question is actually from a professor who's joined us from South Africa, Dr. John. And I think it's a pretty tough question. But anyway, does the muon anomaly, which I think may be the discrepancy of the muon magnetic moment anomaly with the standard model calculation, have any relationship to or way to predict what beyond standard model mu to E conversion might be?
Oh, I don't work on G-2, so I don't work on the muon magnetic anomaly. But we do have some people in the audience who do work on that experiment, so they might be more experts than me. I'm not 100% sure about what implications the magnetic anomaly has on mu to E conversion specifically, but I believe there are some implications for beyond the standard model. And definitely, if we see mu to E, there are many beyond the standard model implications. We can also sort of do some figure out what mechanism is causing beyond the standard model interactions if we do see mu to E using some different tools.
One of those audience members is me, who works on that other experiment. So let's just say that the muon is providing us with mysteries.
Yes.
So that is definitely true. Okay, so here's the question that is sort of a team question. Mackenzie, could you do your experiment underground? And Chami, could you do your experiment with a muon veto that Mackenzie had built?
So I guess I can go first. We can do mu to E underground, but I guess the question is, can you get a muon beam underground, and how much money would that cost? So all of the accelerators that we have, I think, around the world are on the surface of the Earth. So we're really restricted by where our beams are produced, and we can't build a new facility underground. I think that's probably the most important part of mu to E, but if we could get rid of our cosmic ray background and we didn't have to build a cosmic ray veto, we could do a lot better with our sensitivity, potentially.
Okay. That's a great question. And we actually do have a muon veto. It's actually a part of the outer detectors of LZ. As to if we had a super sophisticated muon veto on the surface, could we run LZ on the surface? That I don't think we can, because we'll just have so much background from cosmic rays that we won't be able to see the very infrequent signal of a WIMP.
Okay, and another one for both of you is just to sort of look a little further in the future beyond your experiments. Will there be a future for each of these fields?
Yeah, so I guess I can start. Mu to E, we're still building mu to E, and it's not on yet. It'll come on in a couple of years, but we are already designing a predecessor, or I guess an experiment in the future called mu to E2, where we're improving a lot. So one of the things that we're improving a lot on is the cosmic ray veto. We think that we can get a lot more efficient than a 99.99% reduction efficiency. But in order to do that, we have to design the cosmic ray veto counters, so these scintillators, in a different way. So instead of using like a rectangle here for mu to E, in mu to E2 they actually use triangles so that you have a little bit more granularity on where you can detect cosmic ray muons. There's also upgrades to things like the stopping target. The tracker will get an upgrade. We'll use thinner straws if we can, so that we get better resolution everywhere. Yeah, so we're already designing mu to E2. There's a lot more to go in the mu to E story.
Yeah, same in the case of liquid xenon experiments. You can imagine like an inverted tree where experiments started out small and very numerous. The earliest liquid xenon experiments had active masses of like kilogram scale. And then they joined forces and they built 100 kilogram scale detectors and ton scale detectors, and LZ is a 10-ton detector. So for the future, we are going to be joining forces with other collaborators in Italy and building a super mega big detector that's going to be called Darwin. And talks and planning for that experiment is currently underway.
Okay, great. Well, thanks to both of you. Those are really tremendous talks, wonderful answers. I think everybody will agree as we congratulate them and thank them that the future of science and the future of physics and the future of particle physics is in great hands. Thanks, guys.